Hello everyone, I'm Adbanaki Pratik. I'm going to present our paper, Real-Time Personal Protective Equipment Detection using YOLO V4 and TensorFlow, which was accepted to be presented at 2021 IEEE Regional 10 Symposium, August 23rd to 25th, Jeju, Republic of Korea. The authors of the paper are Adbanaki Pratik, Amjad Hossain Rafi, and Shahnawaz Siddiq. All the authors are from Department of Electrical and Computer Engineering at North South University, Dhaka, Bangladesh. Introduction. The world is witnessing the destruction of COVID-19. According to World Health Organization, around 196 million people have already been confirmed of getting the disease and 4.2 million people have already died of the disease. COVID-19 spreads through close contact with an infected person. The virus enters the human body through mouth, nose, or eyes. Infected person creates respiratory droplets through coughing and sneezing. Respiratory droplets carries the virus. Protective equipment can help stop human-to-human transmission. Some people are reluctant to wear protective equipment. Both infected and non-infected persons without protective equipment helps the virus to spread. It is important to detect the ones with and without protective equipment. In our paper, we developed a system to detect protective equipment. Protective equipment like face mask, face shield, and hand gloves can be detected by the system. Literature review. In Vin et al., her cascade classifier ELF-V3 and data from MAFA dataset were used to detect if someone is wearing a mask or not. In Hari et al., VG19 image classification model has been used to diagnose COVID-19. The model was trained with a combined dataset consisting of 3 modes of images, which are ultrasound, CT scan, and X-ray images. The dataset had lung images of normal pneumonia patients and COVID-19 patients. In Kai et al., faster RCNN model was used to detect objects on the street. The model was already pre-trained with COCO dataset, and to fine-tune the model, it was trained with a custom dataset consisting of images collected from the internet. Data preparation and annotation. We have a combined dataset in the solution. The dataset has collected images from a Kaggle dataset, collected images from Google, and our own captured images. In total, there are 1,392 images. The Kaggle dataset has 853 annotated images. We took 753 annotated images from the Kaggle dataset. We collected another 167 images from Google. On our own, we captured 472 images, 4 classes of images in the combined dataset. The classes are face mask, no face mask, face shield, and hand gloves. We annotated the collected images from Google and also the captured images. Here are some samples from the dataset. We have in total 5,327 annotations for the images. On an average, 3.8 annotations per image. We used a Level IMG image labeling tool for the annotations. We chose YOLO format for the annotations as we are going to train YOLO V4 model. We used RoboFlow framework for training set augmentation. In RoboFlow, we resized all the different images to 416 into 416 dimension. 3 image augmentation techniques were applied on all the training set images. The image augmentation techniques are 15 degrees image rotation of the images in random directions, 1% to 10% cropping of the images, and adjusting color vibrancy of the images. Images of the combined dataset were divided into 70% for train set, 20% for test set, and 10% for validation set. Methodology. We chose the YOLO V4 model for the object detector of the system. We used RoboFlow computer vision developer framework to build the object detector using YOLO V4 model. We used the paper dataset to train YOLO V4 model. We used Google Colab's GPU and other resources for the training. We converted the weight we got in Google Colab to the weight format for TensorFlow platform. Additional features are implemented with real-time PP detection using camera. The system uses deep sort object tracking algorithm to track detected objects. Custom functions were used and other processes were followed to count number of objects detected per class and crop out detections to save them. The system captures the frame after every 150 frames from the real-time camera feed. From the captured frame, the system is able to crop out detection for mask and no mask and save them to keep record. This is the working flow of the system. We can see in the figure that the object detector gets input data, and from the input data, the object detector is able to detect 4 classes of objects. In case of mask or no mask, the system crops out the detection for keeping record, and then object counter counts number of masks or no masks detected. In case of face shield and gloves, the object counter counts number of face shield and gloves detected. Results. We collected a video to use it as an input for the object detector. And then we got the output video. This is the screenshot of the output video where you can see the object detector detected people with and without face mask. This is one part from the output video where you can see that the object detector is able to detect people with and without face mask in real time. This is a screenshot from our captured video. We can see that the object detector was able to detect all the 140 equipment. This is a screenshot from real-time webcam feed. You can see that the object detector is also able to detect all the 140 equipment. The system was counting the number of objects detected per class. This is the average loss and mean average precision graph. We can see in the graph that for the full training of the model with the prepared dataset, the iteration started from zero. The training started from zero iteration and continued until 8,000 iterations. The MEP of 52% was calculated at around 1,000 iterations. At that moment, the average loss was well above 4.5. The average loss went under 4.5 at around 1,600 iterations. The MEP went above 70% at around 1,920 iterations. You can see during the training from time to time, the average loss and MEP was fluctuating. The average loss, the lowest average loss of approximately 2.1 was calculated at around 7,500 iterations. The highest MEP of 79% was calculated at the end of the training. After the training ended, we got MEP of 79% and the average loss was approximately 2.97. These are the average precision of the classes. Average precision tells about correct predictions that a particular class made. Here you can see that the mask on class had 86.92% average precision, no mask class had 73.08% average precision, face shield on class had 84.56% average precision, gloves on class had 71.53% average precision. These are the model performance evaluation metrics. Precision refers to accuracy of the predictions made by a model. Recall measures the ability to find positive cases by a model. F1 score takes precision and recall both into account and is a weighted average of them. The precision of the model was 78%, the recall of the model was 80%, and the F1 score of the model was 79%. Conclusion. We have a combined dataset in the solution which includes collected images as well as our captured images. In the solution, image augmentation techniques have been used. The system can do live object detection. We have implemented additional features like live object count and keeping records in TensorFlow. We got promising results from different evaluations. Real-time object detection model ELF4 has been used for the solution so that it can be implemented in PP monitoring systems for COVID-19 or any other disease which spreads the same way. Thank you, everyone.